Hey, welcome back to Short Takes 331. Today, we're going to talk about how to diagonalize differential operators on the lattice. And to that end, we start with a question. So how do we represent functions on a computer? And here, we should really think that memory on a computer comes in discrete units. So you don't have a continuous real line to represent your function f of x, neither on the domain nor on the image. So we don't have a continuous set of values for f, and we don't have a continuous set of values for x. So really, our memory is sort of going to look like this. Every time we want to evaluate the function at a particular point, all we're going to have at our disposal is the function at the discrete set of points. And this is true, for example, when you make a plot. If you ask the program like Mathematica, for example, to make a plot, then what it will do is will give you a very fine mesh of values or a very fine lattice of values of x, and then it will evaluate the function at those values. And those are very, very fine values, very finely separated values, so you won't really see anything other than a nice continuous curve that looks very smooth. But of course, in reality, that's not true. In reality, when you go and you look very fine at the details, then there's some separation between the values of x. So because of that separation, then the values of f are also discretized. And so we can accumulate then the values of f and assemble them into a vector like this. And this is what we're going to think about when we talk about functions in this video. So we're going to imagine that our function is given by a vector, which could be very long, but it's a vector of n components that stores the values of f at the values of the domain x1, x2, x3, and so on, all the way to xn. This is going to be our x lattice, and so our f is encoded into this vector, so it's the value of f at the various points on the lattice. And we could simply call them f1, f2, all the way to fn as the entries of this vector. And so that's how we're going to think about the function. Now, we're interested here today in talking about derivatives of the function. So we want to talk about differential operators. And so how we're going to represent that on the lattice. This is a bit of a problem, and it's solved by making approximations. The definition of a derivative of a function with respect to a variable x is the limit when the spacing goes to 0 of f at x plus h, the spacing h minus f of x, all divided by the spacing h. And when you take the limit of h going to 0, then you recover that rate of change of the function at a point x. So that's the old Newtonian definition, if you want, of the derivative. Now, on the lattice, of course, we cannot do this, at least not right away, because if we're on the lattice, then h is finite. So we have a finite spacing between the various points. And so on the lattice, what we do is we represent this as a kind of approximation. And there are many ways to do this. Today, we're going to be talking about a particular case, a particular type of representing this limit before we actually take the limit, and that's called this forward derivative formula, which is the function evaluated at the next point over I plus 1 minus the function at the point where you're sitting, fx of I, divided by the difference in distance, so the distance between those points, and so I plus 1 minus xi. And so what we're doing, for example, is we're taking if we're interested in the derivative at this point, then what we will do is we will imagine that we're taking the function at this point minus the function at this point divided by the difference between these 2 points. So this distance, x4 minus x3, for example, in this case. And if we're assuming that our lattice is uniform, which is sort of what I tried to represent here using just 2 squares for the spacing between each of the x's, and we call that L, then we'll say we have a uniform lattice. That L is our lattice spacing, and then f of I plus 1 minus f of I divided by L is what represents this quantity we call the forward derivative. And you see it looks very similar to what we have here, except that we're not taking the limit L going to 0, or at least not yet. Maybe one could imagine that one does calculations of this type for smaller and smaller L, but for now we're going to imagine that we're working at constant lattice spacing L, and that we have a uniform lattice, and so the spacing is the same for every pair of points x1, x2, x2, x3, and so on. Every consecutive pair of points has the same lattice spacing L. Now, this is the formula, if you want. For a given point I, we would calculate fi plus 1 minus fi divided by L, but we can represent that very conveniently as a linear operator, which is what the derivative is. If you recall our discussion of linear operators a few videos back, you'll find that we gave the derivative as an example of a linear operator, and as such, it can be represented as a matrix. And in this case, our matrix is going to take this form. There's going to be 1 over L factor, which of course this is 1 over L here. And then there's going to be minus 1s in the diagonal. And that makes perfect sense because we have that when we apply our operator to our function, then we return something that goes like I plus 1, but then there's a minus sign and the same thing that we had before. So f, and so that's the reason for these minus 1s. And then this first term is represented by this off-diagonal points that go like all ones on the upper diagonal. By the way, this should be a 1 here. It should not be a 0, it should be a 1. So it's minus 1s on the diagonal, and then 1s in the top diagonal here, the one off diagonal part of the matrix, and then we have 1 here on the other side. And so what is the meaning of that? So there's 0 everywhere else, but there's a 1 here, and the meaning of that in this n by n representation of the derivative is that that's a boundary condition. And so here we would need to put a 1 to the right of each minus 1. So there's a 1 to the right of the minus 1. There's a 1 to the right of this minus 1. So what happens to the right of this minus 1? Well, there's no more matrix. And so we go back to the beginning here. And that's what we call periodic boundary conditions. And it amounts to imagining that our domain, instead of going just from 1 to n like this and continuing nowhere, it's closed into a loop. And so we go from 1 all the way to n. And when you try to evaluate n plus 1, you go back to 1. So that's what we call a periodic boundary condition. And if you wanted to somehow represent a very long line, then you would take n to be very large, and that would approximate the idea of having a uniform systems where the boundaries are very far away. And this is our function encoded into a vector, as I mentioned before. And so if you were to do this calculation, you will find that you get a 1 over L times minus f1 plus f2, and that would of course be the result corresponding to the derivative applied to the point f1. And so, or rather applied to the function, but it would be the derivative at f1. And then the next one over would be f3 minus f2 divided by L. So f minus f2 plus f3 divided by L, and that will give you the next component of the derivative and so on. And when you get to the end, what you will have is minus fn plus f1, the whole thing divided by L, and that will give you this, again, this quantity corresponding to the last point, assuming periodic boundary conditions. And so this is then a representation in matrix form of our first derivative operator. And I encourage you to put an equal sign here and by yourself go ahead and carry out all those differences and see what they look like. The first component, again, it's going to be f2 minus f1 divided by L, then f3 minus f2 divided by L, and so on and so forth. And the last one is going to be f1 minus fn divided by L. You should check that. And this is one of the nice things about this this matrix form or thinking about differential operators in matrix form. That is that you really need to consider the boundary conditions as part of the matrix. So this is all one thing. It's not only the differential operator, it's also the boundaries and what we do at the boundaries. There are other types of boundary conditions that you may want to consider for physical reasons, for mathematical reasons. If you put a 0 here, you would have something that you might call a hard wall boundary condition. That is also important in many applications. In this case, we're going to focus on the periodic boundary conditions that when you get to n, the next point over is 1. It's the initial point that you started with. So this comes with the matrix. Is not usually the case. When you solve differential equations, actually, you need to think about these two things separately. So one thing is a differential operator that takes derivatives locally, and then another thing is what happens at the boundaries. Well, it's not the case when we represent things on a computer. You have to think about the matrix that gives you the differential operator all as one thing that also includes whatever happens at the boundaries. Now, with that in hand, it's very interesting to notice that if you take that matrix and you apply it to a constant vector, you get 0. And it makes sense. So what this is going to do is going to subtract components that are next to each other. And if the components are all the same, then you're just going to get 0, 0, 0, 0 everywhere. And that makes sense because also it is the derivative of a constant. And the derivative of a constant function is just 0. This function represented here is a function whose components are all constant, and the derivative of a constant is 0, and so that's perfectly okay. That's exactly what we should expect to get, and this is true for any constant. So this operator applied to any constant, it could be all ones or all sevens or all pi's or whatever you want, all that will give you all zeros. So this tells us that the kernel of our operator is non-trivial. So the set of vectors that make the result vanish is non-trivial. It's not just a zero vector. Of course, if we put a bunch of zeros, you get zero. But also other constants give you non-zero. And so this tells us that we don't have a well-defined inverse. In other words, we would find, if you were to take the determinant of this matrix, that it would actually be zero. And so as written here, it's not invertible. We would need to do something else. We need to regularize it in some fashion and change it in some way to make it invertible. I will leave that for a future discussion. But for now, you can also check out that this way of writing the matrix actually works out and it gives you the right answer. So if we take the matrix elements ij of d1, we get 1 over L times minus delta ij plus delta I plus 1 j. And that simply, this part represents the diagonal, and this part here represents the off diagonal of the matrix. So the ones and the minus ones, all the minus ones on the diagonal, all the ones here. Remember, there should be a 1 here. That was my mistake. And then there's this 1 here of the periodic boundary conditions would be accounted for by using periodic indexing. In other words, when I is n and we have to evaluate at n plus 1, we regard that to be 1. In other words, we take the integers modulo n, if you want a more precise way of saying this. But this is enough for us to represent the periodic, the structure, not the periodic part, unless you consider this, of course, but all the structure of the matrix. So the minus ones on the diagonal and the ones in the off diagonal. And that is very useful because we will see now what happens when we apply the matrix to a very special vector v sub k. And of course, I'm talking here about nothing other than the vectors that define the Fourier transform that we described in the last couple of videos. So we're going to call this v sub k element j to be 1 over square root n and exponential of I 2 pi over n k times j. So these are our elements of our vector. The this vector has an index k, which is a vector index. So there'll be several vectors. So k goes from 1 to n, and these vectors will have indices j or components j that give you this formula, that are given by this formula. And so what happens when we apply our derivative operator to this object? Well, let's do that. So we take the derivative operator, we apply it to v sub k, and we calculate the qth element of that result. So the result of applying the matrix to a vector will give us a vector, and so that vector will have components. So q is one of those components, and the result of doing this calculation is simply the sum from j equal to 1 to n, 1 over L, and then we have minus delta qj plus delta q plus 1j, and 1 over square root n coming from here, and the exponential that we had before. So here I've done nothing other than just taking this formula for the matrix elements for operator. I renamed the index I to avoid confusion with this imaginary unit, but then I put next to it this vector, and now what we need to do is construct the contraction over the index j. So we're summing over j. So that sum over j, what's going to do is, for this first term, delta qj, is going to replace every j with a q, and so we get this result from that with a minus sign, as you see there. And then for the second delta here is going to, when we do the sum, we're going to replace every j with q plus 1, and so that's what we get here. We replace j with q plus 1. That's the effect of the Kronecker delta. And this square root of n is here, and the 1 over L is here, and everything else is all right there. And so the next thing that we're going to do is we're going to simplify this a little bit. I'm going to pull out this exponential of I 2 pi over n q times k as a common factor. It's the same that appears here, q times k, but then there's the plus 1 here, and this plus 1 is simply e to the I 2 pi over n k as multiplying this object. Remember that the sum and the exponent is just a product of the two separate things, one accounting for the q and one accounting for the plus 1. And so the one accounting for the 1 is what I have here. And then this minus 1 comes from this minus sign here. And all that is simply multiplying the 1 over square root n exponential of I 2 pi over n k times q. So this is written like this on purpose. I reorganized the terms a little bit, but really there's very simple math here. And so what we get at the end of the day is 1 over L this term in brackets, which depends only on k, but not on q. It depends only on k. And then the vector that I started with. If you look at this carefully, you see it's the same guy. It's vk element q. So it's the same thing that I started with. So in other words, it's the vk element q. And so what this is telling us is that applying our matrix D to a vector returns the same vector as a result times a constant in front. And that constant depends on which vector you're talking about, because the vectors are indexed by k. But the bottom line is simple, and it's simply telling us that vk is an eigenvector of this derivative operator that we constructed before, the one that takes this form here, and with eigenvalue lambda k given by 1 over L, and then this term in brackets exponential of I2 pi over n k minus 1. So that's telling us that Fourier modes are eigenvectors of the derivative operator, and other derivative operators as well, not just the first one, also second derivatives have the same eigenvectors. And these are what I call Fourier modes here. If you fix J and you if you fix K and you vary J, although that's also true vice versa, but if you fix a given mode K and you vary J, then you obtain the behavior of a Fourier mode. Now, this works for periodic boundary conditions. If you had other boundary conditions like hard walls and so on, you have to construct the modes in a different way. And if you make the boundary conditions very complicated, like if you're in higher dimensions, then you have to work a little harder, perhaps considerably harder, but this is always generally true, that these differential operators will have some special modes that are generalized Fourier modes, or in this case, pretty standard Fourier modes that are their eigenvectors, and they will have some, those will have some eigenvalues. The result, of course, will depend on the boundaries, is what I'm saying. Now, notice something interesting. If I put k to n here, I get e to the I 2 pi. The n cancels with this n, and e to the I 2 pi minus 1, which is 0. So that is lambda n then is 0. And it also, if you put n in our formula for v sub k, you obtain a constant vector, which is 1 over square root of n. So the exponential of e to the I 2 pi times any integer, so now that the n has been cancelled by the k being equal to n, then that's going to give you a 1, and so this exponential of that is going to give you 1, and so you are left with 1 over square root of n, which is just a constant, which again is consistent with what we said before, that our matrix applied to a constant vector is going to give us 0. So that's one of the modes then is what's called a zero mode. It corresponds to a 0 eigenvalue, and this is again the reason why we cannot invert this operator, at least not as written here at face value, because we have that the determinant is 0, because there's a lambda n, or there's a lambda that vanishes. Finally, and to finally get to the point of the diagonalization, if you take d1 applied to vk, you obtain, like we said up here, you obtain lambda k vk. But if you sandwich that with vk prime dagger, then we know that vk dagger and vk are orthonormal to each other. We know that from a calculation we did in the last video or the one before. So if you haven't watched those, you should go and check them out. The point is, we will get lambda k times delta kk prime. In other words, we've managed to find the eigenvectors of our differential operator, and so when you sandwich your differential operator between those two such eigenvectors, you obtain lambda k delta kk prime, which is the diagonal form of the matrix of the operator d of 1. More specifically, this is really the diagonalization identity. U is going to be given by our eigenvectors in columns. And when you make u dagger d of 1 u, you obtain a matrix that is diagonal, that I just called d, as opposed to, not to be confused with d of 1. d1 is just the first derivative, but this d is a diagonal matrix whose diagonal then is given by all the eigenvalues, lambda 1 through lambda n. As we just saw, this last lambda n is actually 0, and so the determinant of this matrix will be 0. And so we obtain then that the determinant of our operator is 0. And then finally, written in full form, the elements of our diagonalizing matrix, that are unitary matrix U, are given by this. ukj is 1 over square root n into the I 2 pi over n k times j, which is our old Fourier matrix, once again, which we saw in the last couple of videos. This is, in a nutshell, how do you diagonalize operators, differential operators in systems with periodic boundary conditions that are put on a lattice. The Fourier modes are simply given by this formula that we saw before, and then if you sandwich your operator between u and u dagger in this way, then you obtain the diagonal form of your operator. If you enjoyed this video, please like and subscribe. If you're looking for a tutor in physics or math in English or in Spanish, maybe I can help you. You can contact me at shorttakes331@gmail.com, or you can leave a comment in the comment section below. And I will see you next time.